Alright, so we're going to try to get more information from our frequency distribution. And we're going to try to define some things. So here I pulled our frequency distribution over. And what we kind of want to notice is because each of these classes have the same width, there is a middle point to this class. And the midpoint follows the midpoint formula, where you take the lower class limit plus the upper class limit and divide by 2. So for example, the first class, 155 plus 190 divided by 2 gives us a midpoint of 172.5. Right? This is calculator time. And so I'll add these two numbers, divide by 2, add these two numbers, divide by 2. So the midpoint here is 172.5, 208.5, 244.5, 280.5, 316.5, 352.5, and 388.5. Oops, 388. Yeah, it's big. And so I'll just put midpoint up here. It's a good reference for things when we're graphing, to know where the middle of it is. And it's also a good way of talking about that class as a value. It generally is the midpoint. And we'll look at that more as we build our statistics out. Now if we remember, the sum of all of our frequencies was equal to 30, which was the same as the total pieces of data that we had. Well, I can talk about what we're going to call the relative frequency, which is the frequency divided by the number of pieces of data in the data set. So for the first one here, it's going to be, I'll put it down here, f over n, and I'll put a subscript 1 for my first piece of data. That's 3 divided by 30, which is 0.1. And so the relative frequency is 0.1. Now one of the things you'll get with me is 0.1, I'm going to add another decimal place to it. I see this or say this as 10%, because 10% of our data is here. Right? If we want to change this to a percentage, we multiply by 100. This is 10%. You'll find in statistics, especially inferential statistics, when we're using a percentage, we'll use the decimal version of it. So a lot of times I'll write this and I'll go, hey, this is 10%. And I'll leave it as a decimal, because later when I go to use it, I'm going to multiply by this number. But let's look at the second piece of data. Over n is 2 over 30, which is approximately 0.07 or 7%. And we're going to round to 2 decimal places here. Depending on the problem, rounding to 2 decimal places, it really depends on what we're looking for. So on the calculator, 5 divided by 30 rounds to 0.17 or 17%. 6 divided by 30 is 0.20. 7 divided by 30 is 0.23. 4 divided by 30 is 0.13. And this we already did up here. 3 divided by 30 is 0.10. And these are the relative frequencies. They tell us approximately how much is there. Because we've rounded, the approximately comes through. Now, if I were to have written down, and I'm just going to put over here the fractions, 3 over 30, 2 over 30, I'm not going to simplify it. 5 over 30, 6 over 30, 7 over 30, 4 over 30, and 3 over 30. Because I did not round these add up to 1. Or 1 in percentage is 100% of my data. And this is a good double check. What's really, really nice is when we want to infer about a larger population. If this is my sample, little n sample, and my larger population was 500, I could infer that about 10% or 50, because 10% of 500 is 50, of this population would be in the first class, in the value, which is the drug, if we read the question, was the out-of-pocket drug expenses. And so relative frequencies are actually a really good inferential statistics tool. The fractional parts will always add back up to 1 if we keep the fractions. The decimal parts, because we round, that's not always guaranteed, but they'll be close. In this case, we rounded up twice and we rounded down twice, so this does add up back up to 1. But in general, that's not always the case. All right, what I'm going to do here is I'm going to clean out the fraction part here. Give me a second. Just erase these out. And there's another thing we can keep track of, and this is called the cumulative frequency. Cumulative means to add up. And what we want to do is we want to add up how many things have happened. So I'm just going to put cumulative frequency, C-U-M-U-L, oops. There we go, cumulative frequency. And so when we start, if we have a value less than 155, well, we have no data there. So we start with 0, and when we get to our first class, we look at how much is in our frequency, and we add that to our cumulative frequency. And then we take our next class, and we say, well, I've got 2 more. So 2 more than 3 is 5. I've got 5 more, it's 10. I've got 6 more, it's 16. I've got 7 more, it's 23, 27, and 30. The cumulative frequency of the last class should equal the total number of pieces of data. And this tells me that if I am on this class here, I've got 10 pieces of data for everything below. It tells me how many things have come before. And so if I get to this class here, I've got 27 pieces of data from the upper class limit all the way down to my starting point. And so the cumulative frequency is a way of showing how much has come before, or how much there is before. And so one of the things we can kind of look at in this data set, and we'll see this more when we make this graphical, because that's going to be my next step, is to turn this frequency distribution into a graphics. But well, right here, 16 is slightly more than 50%. So 50% of the data comes before here. But if we look here, right, 20, 23, and 17, 50% of the data, more than 50%, right? It's at 43, 60% of the data is within these 3 chunks here. And what we want to do is turn what these numbers can represent into a graphical representation. Some way of saying, hey, where does all the data lie? And the tool we're going to use is called a histogram. And in the next video, I'll bring in a histogram for us.